Hey guys, so today we're going to be talking about EMF, which is the electromotive force, and terminal voltage. So I'm just going to write out the equation that relates the two, and then I'm going to explain units. So V in this equation is equal to the terminal voltage. So the terminal voltage equals the EMF minus the current times by the internal resistance. And if we think back to Ohm's law, V equals IR, or or the current measured in amps times by the resistance measured in ohms equals volts. So this whole thing is going to be measured in volts. Same with the EMF, it's measured in volts. And then we've got our terminal voltage here. So I'm going to use an analogy first to see if that helps explain EMF, or the electromotive force. So we know that at the top of a hill, a car has some potential energy. Let's say in this instance, the potential energy is equal to 120 kilojoules. So this car travels down the hill. As it's traveling down the hill, some of this energy, some of the 120 kilojoules, dissipates as heat. So we'll just say for our purposes today that that's 1 kilojoule dissipates as heat. So at the bottom of the hill, instead of having 120 kilojoules, this car has a kinetic energy of, let's say, 119 kilojoules. So if we're looking at a battery has a negative side, or a source of electrons, and that's flowing to the positive side, so the flow is this way. So in a battery, let's say that the negative end has an affinity for the positive end of 12 volts. Well, this battery also has an internal resistance, so the actual output will only be like 11.5 volts. So just like the car, or I guess the wheels against the road, some energy was converted to heat, which is why if you felt a battery that's being used, it actually heats up. That's because there's an internal resistance. So the important part here is that this 12 volts is the electromotive force. That's the EMF. And this 11.5 volts, the voltage or the power that is actually supplied to the system, is only going to be 11.5 volts because of the internal resistance of the battery again. Okay, so let's say we've got, I'm just going to draw a quick circuit diagram so we can get an idea of how these work. So we've got E, which is our electromotive force. We've got our internal resistance, and then we've got our resistor. So a battery has essentially two parts. So this entire thing is a battery. So battery has two parts, which is the energy source. There's a positive end and a negative end. And in physics, we just use the convention of drawing current flowing from the positive end to the negative end. So we've got our energy source, and then we've also got our internal resistance of the battery. And then we've got a resistor. That's going to be something like, I don't know, like a light bulb here. Okay. Something that's kind of interesting, it's not it's not central to this video, but it is good to know. A car battery will have, let's say we've got a car battery here with 12 volts, and then we've got a motorcycle battery here with 12 volts. So they both supply 12 volts. But if we look at Ohm's law, even though voltage source is the same, in a car battery, the internal or the current is going to be greater than the smaller battery, and therefore it's going to have a smaller resistance, or in this case, it's going to have a smaller internal resistance. Whereas the motorcycle battery, it's going to have a smaller current and therefore a higher resistance. So if this were being supplied to power to a circuit, this might have like 11.9 volts being supplied to the system, whereas this one might only have like 11.5 volts. So again, this is the EMF, this is the EMF, this is the terminal voltage. So the terminal voltage is what's actually being supplied to the system again. Okay. So now if we're going into, so I said earlier that relating the two equations, we've got V equals EMF minus IR. So this I is the current of the whole system. So if we've got, let's say, we've got our example here, got our circuit diagram. We're going to say that this E here is 2.3 volts. So that's going to be our EMF. Our voltage being supplied to the whole system is going to be 2 volts, or that's our terminal voltage. We've got our internal resistance. We're going to say that's what we're trying to find. And then this is going to be equal to 4 ohms equals the resistor, or the resistance of the resistor. Okay, so now when we're going about this problem, we have to find what the total current of the system is, and then we can use that. We have our terminal voltage, we have EMF, then we can find our internal resistance of the battery. Okay. Let's show that equation. So we're just going to use Ohm's law, say V equals IR, since we're trying to find this. So we're going to say that 2 volts is what's actually being supplied to the system, our terminal voltage. I is going to be equal, well, that's what we're looking for, and then R is equal to 4. So we find that I equals 0.5 amps. Okay, so that's going to become important in just a second. We're going to use that. And then we can see that our EMF, so our EMF is 2.3 volts. Our terminal voltage is 2 volts, which means so sorry, we're using this equation right here now. So we're going to go back actually. So our terminal voltage is 2.3, or 2, sorry, terminal voltage is 2. Our EMF is 2.3 volts, and then minus internal resistance, which we just found to be 0.5. And then we are looking for R. So if we do this, we subtract 2.3 from both sides, subtract 2.3, we're going to get negative 0.3 is equal to negative 0.58 times by R. And then when we're dividing both sides by negative 0.5, we're going to find R to be 0.6 ohms. So there's our internal resistance of the battery. And then that is our solution to that problem. So I'm just going to zoom out for a second here so you can get an overview of everything that we just went through. And then, so that is my video on EMF and terminal voltage. Thanks for watching, guys. We'll see ya.